So today, class 12th electrostatics, we are going to have 7th lecture on this, which is very important concept. And the concept is all out electric flux, area vector, and Gaussian surface. When we talk about electric flux, it means total number of field lines passing normally over a surface. And mathematically we write it, or it is measured as d phi is equal to E ds cos theta. So if we integrate d phi, integration will give us phi, and ds integrated gives us s. And because it is passing normally, so angle between surface area and electric field is 0. So cos 0 is 1. Thus we get phi is equal to E into ds or E into s. So this becomes the formula. So let us find the unit or SI unit of phi, flux, electric flux. So electric field would be Newton divided by Coulomb into S per meter square. So Newton Coulomb inverse meter square. Then second concept is area vector. In general, area is a scalar quantity. But when we take very small portion of a surface that is supposed to be a vector, it is mathematical convenience. It doesn't mean that area becomes a vector quantity. So if ds is a small surface area, then we may write ds and into n cap. N cap gives the direction along the surface itself. And then the third concept is Gaussian surface. In general, electric field varies with the distance, that is E proportional to 1 upon r square. So when you move from a charge, then electric field decreases. But if we call a Gaussian surface, then it is an imaginary surface around a charge over which net electric field is always constant. So these are the few basics before the Gauss law. So let's come to the Gauss law now. So far Gauss law is concerned, this is all about the again measurement of the electric flux only. So according to Gauss law, the total flux over a surface is equal to 1 upon epsilon naught times total charge enclosed in the surface. So again, this is measurement of flux, but in terms of charge and epsilon naught. So phi is q upon epsilon naught, mathematical form. Also, if you want, you can write like this. Since phi is equal to E ds cos theta, we have already done. Line integration is equal to q upon epsilon naught in extended form. This is mathematical form of Gauss law. Now the point is the applications of Gauss law. When we come to the applications, we have first and foremost application, which is the electric field due to a line charge. Line charge means a substance which is linear in shape. Let's say this one. This is linear. If it is a conductor having uniform charge distribution, which means plus, 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 plus. Now around this, let's say we select a point P which is at certain distance r. We want electric field. Doesn't mean that only at this point field would be effective. So there can be so many symmetrical points around this charge or above this line charge. But what about the lower portion of this line charge? Here also electric field would be effective. So let's join this imaginary surface, and when we join this imaginary surface, this surface becomes a Gaussian surface. Now this Gaussian surface is like a cylinder, and the next step starts that a cylinder having three surfaces, top, bottom, and then the curved one. When we talk about the top and bottom, which are identical, so let's decide the direction of electric field and area vectors. We select small part of this. This is significant because in general, bigger portion of any surface is scalar. So smaller part, we can call it ds, ds cap. And because this is positive, line-like, so charge is not effective this side, right side. I mean electric field. Electric field would be either up or down. So this is the direction of field over here. Thus, we have determined the direction of electric field and area vector, which is at 90 degree to each other. Obviously, on the opposite side, this would be ds. So ds cap and field remains same. This is E vector. Now this is 90. So far this curved surface is concerned, again we take small part of this. Why? Already explained, because ds small portion only is a vector quantity or can be considered as vector. So far field is concerned, field is also acting along the same line. So only due to the curved portion we see ds and E are acting along the same line. Because in the formula we have E ds cos theta. So cos 0, so maximum flux would be contributed, but net flux would be contributed due to this curved surface only, which means the other two portion top and bottom are not contributing to any flux. Now the net flux phi is equal to, let's write phi 1 plus phi 2 plus phi 3 due to three surfaces. And then if you write like phi, so phi 1, let's take this surface left side as first surface, curved surface as second surface, and right side one as the third surface. So phi 1, it will be E ds1 cos 90 line integration plus second surface we are taking curved one. So we write E ds2 cos 0 plus again third, so E ds3 cos 90 integration. And now if we solve, what we get? Phi is equal to cos 90 is 1 or 0, cos 90 0. So this becomes 0 plus cos 0 is 1. So this becomes ES. This is also 0. So it is ES, equation 1. And also from Gauss law, phi is equal to, we have already done, Q upon epsilon naught. But we know the linear charge density lambda is Q upon charge per unit surface area. So S. So Q can be lambda into S. So we write lambda into S upon epsilon naught and equation number 2. So from equation 1 and 2, what we get? from equation 1 and 2. It will be Es is equal to lambda s upon epsilon naught. So we see that the